Hello everyone. I am Guru Charan from RV College of Engineering, first year Electronics and Communication Department. Today in this video, we are presenting our first phase EL topic for the chemistry cycle. Next slide, please. So these are the details of our teammates. Next slide. So as a part of our EL, we are talking about development of an Arduino-based LED photometer. So we know that in the recent times, heavy metals are causing a serious threat to the environment. And since they are non-biodegradable and have a higher tendency to accumulate in the living organism, they are a potential carcinogens. So it is very important to detect them even in the trace quantities. So there are many sophisticated methods for the detection of the heavy metals, but sophisticated methods cannot be accessed at every point of time. So we need to develop a simpler method that can be used to detect the heavy metals at all times. So photometry is one of the principles that we can use to detect the heavy metals in a simpler way. Next slide, please. So photometry is a principle that is used to describe the properties of the light, like color, radiation characteristics, color temperature, color rendering index, etc. Next. Colorimetry is a branch of photometric principles that is useful for determination of the heavy metals. As the name suggests, colorimetry is based on the color that the heavy metal forms with chromogenic agents. Chromogenic agent is basically the chemicals when mixed with the heavy metals forms a colored solution of the respective heavy metal. So this colorimetry is based on the Beer-Lambert's law, which states that concentration of the solute is directly proportional to the absorbance. Next. Principle of photometer. Most of the photometer detect the light with the photoresistors or the photodiodes or photomultipliers. To analyze the light, the photometers may measure the light after it has passed through a filter or a monochromator for the determination of the defined wavelength, or for the analysis of a simpler distribution of the light, spectral distribution of the light. These are some of the images of the photometers or the colorimeters that are available in the market. Next slide. So coming to the working of photometers, this is the block diagram of the working of the photometers. So basically what it says is when a light, basically we use a LED source of light. When passed through a slit or the aperture, it narrows down the field of the light, and then it is passed through the condenser lenses, followed by filters, and then it is made to incident on the cuvette containing the sample. So this sample absorbs some of the light and then transmits the remaining light. And when the transmitted light falls on the photo detector, it generates a corresponding voltage through which we can measure the absorbance of the light. So if the concentration of the solution is greater, then more light will be absorbed, which can be identified by measuring the difference between the amount of the light at the origin and that passing through the solution. Next slide. So photometers can be used for in two ways. Either we can detect which metal is present in the sample, or if we know which metal is present in a sample previously, we can determine the concentration of the heavy metal that is present in the sample. So when a monochromatic beam of light of intensity I0 is incident on a medium, then a part of the light is absorbed by the medium, and then the remaining is transmitted, and some part is also reflected. So we can represent, if we represent the initial intensity of the light as I0 and the absorbed energy of the incident light as IA and transmitted energy as IT, reflected energy as IR, we can express it as I0 is equal to IA plus IT plus IR. So when the medium is completely transparent, we can ignore the IR part, that is the reflected part, and we can write it as I naught is equal to IA plus IT. The ratio of the transmitted light, intensity of the transmitted light to the intensity of the original incident light is called as the transmittance. And if we take the logarithm of this ratio, it is called as the absorbance. The relationship between the absorbance concentration of the medium and the path length or the thickness of the medium is referred by the Beer-Lambert's law as A is equal to epsilon CL, where A is the absorbance, C is the concentration of the sample that is present in the cuvette, and L is the thickness of the cuvette, or it is also called as the path length of the medium. So when we have to find the concentration of the unknown solution, we have to measure the absorbance of different standard solutions and then plot the graph of absorbance versus the concentration. And then we have to find the absorbance of the unknown solution. Then when we match the absorbance from the graph, we can find out the concentration of the unknown solution. So this is about the working of the photometer, colorimeter, and using the photometer to measure the concentration of the metal ion in unknown solution. So next, the proceeding section will be continued by my friend Madhusudan. Next slide.
Yeah. Hello everyone, my name is Madhusudan. I am also from same department. Another application of this photometer is to find the band gap of a material. Basically, band gap of a material is distance between the valence band of electrons and the conduction band. In this picture, you can see the outermost shell of an electron is called the valence shell, and any other band which is present outside the valence shell is called conduction band. When the electron jumps from the valence shell to the next energy level, it is free to conduct. It means it is free to move around the space. Next, please. Yeah, essentially this band gap represents the minimum energy required for the electron to jump from this valence band to the conduction band. As you can see in this picture, the initially all the electrons are in the valence band, and when the sufficient energy is provided to them, they transfer or transmit from valence band to conduction band. This difference between this energy between the conduction band and the valence band and the conduction band is called the band gap. Next slide. Now, the band gap is different for different materials. Based on the energy, band gap energy, materials are classified into three parts, mainly conductor, semiconductor, and insulator. In conductor, as you can see in the picture, the conduction band and the valence band overlap with each other. There is no gap between them. So essentially, the electrons are free to move away, are very free and can move away throughout the space, and there is no energy required for them to transfer from conduction valence band to conduction band. So basically, conductors are very good conductors of electricity. Then the next is insulator. As you can see in the third part of the diagram, the band gap or the distance between the valence band and the conduction band is too large. Therefore, we have to supply more energy, or the at normal conditions, the sufficient energy is not available for the electrons to transfer from valence band to conduction band. So the conduction is not possible in the insulator. Next, the semiconductor. This semiconductor is an intermediate between the metal and the insulator. In semiconductor, the energy gap is not too less and not too great. Means it lies in intermediate level. When a sufficient energy is provided to the semiconductor, the electrons jump from valence band to the conduction band and then starts conducting electricity. These are the three types of materials based on which based on band gap which are divided. Next slide, please. Yeah. Now, band gap can be differentiated two types. There is a direct band gap and indirect band gap. This differentiation is done on the basis of transfer of electrons. How the electrons are transferred. Next, yeah. As you can see, in direct band gap energy, the bottom of the conduction band and the top of the valence band lies in the same value of k. In this graph, you can see the y-axis represents the energy and x-axis represents the k. The k is nothing but it is related to the momentum of the particle. As you can see in direct energy band, the electron jumps from conduction band, valence band to conduction band and stays there, and it also transfers from conduction band to the valence band, releasing a certain amount of radiative energy. In this is the main part of the direct band. The energy released is radiative in nature, and in indirect band gap, the k value is conduction band and the valence band are not matching. So in order for electron to transfer from conduction band to valence band, the electron first has to first has to conserve its momentum. Therefore, a new like phenomenon is occurring, that is a phenon is phenon is created. A phenon is nothing but a vibrational energy which makes sure that the momentum is conserved when the electron transfer occurs between conduction band and the valence band. In indirect energy, top of the valence band and bottom of the band lies at different value scale, and it has to change its energy as well as wave vector. Means when the electron jumps from conduction band to valence band, not only radiative energy is liberated, in with that heat energy is also liberated. So the examples of direct band gap energy are germanium arsenide semiconductor, and indirect band gap energies are silicon and germanium semiconductors. Next slide, please. So to measure this band gap, we have different types of methods. Now another this PPT this project we are going to deal about UV visible light spectroscopy. UV visible spectroscopy is analytical technique that measures the amount of discrete wavelengths or different wavelengths of UV or visible light that are absorbed or transmitted through a sample in comparison to the reference or blank sample. This nothing but when you pass a certain wavelength of light through a sample, the how much of the wavelength or which part of the wavelength is absorbed and which part is transmitted. Based on that spectrum, we are going to find the band gap of that material. As you can see, this property is influenced by sample composition, potentially dividing the information for what the sample is and what the concentration. The main components which are next please. The main components which are required for spectrometers are the light source. Light source is nothing but a light-based technique. A steady source able to emit light across a wide range of wavelength is essential. A single xenon lamp is commonly used as a high-intensity light source for both UV and visible ranges. Xenon lamps are, however, associated with higher costs and are less stable in comparison to tungsten and halogen lamps. And wavelength selection is also important to get to know which wavelength we are dealing with, and in the different wavelengths are monochromator, absorption filters, interference filters, cutoff filters, and band pass filters. These are the filters which are used to filter out the wavelength which has to be transmitted through the sample. Now, the next step is sample analysis. The sample analysis, it may contain an unknown material in which you have to find the band gap of it, or it can contain any other material in which you can find the composition as it. It is similar to the method as explained before by my friend Guru Charan. Then we have a detector which detects the after the light has passed through the sample. A detector is used to convert the light into readable electronic signal. Generally, detectors are based on photoelectronic coatings of semiconductors. Next is a computer for signal processing and output. In this, we are taking the information from the detector and making it in a digital form, so we can analyze and analyze the readings and uh, plot the plot the absorbance versus wavelength graph. This graph here shows the absorbance factor and the wavelength of a material. As you can see, as wavelength increases, first the absorbance is low. At one particular wavelength, the absorbance is high, and again it decreases. And every material has a different pattern of this absorbance and wavelength graph. From this, we can detect a material and also find the wavelength by a method called talk method, which is in the next slide. Yeah, calculation of band gap using talk method. A talk plot shows shows the quality HV in the x-axis and the quantity alpha h square. Alpha is the absorbance coefficient here, and h mu is the energy of the photon. Next, please. Yeah, this is the equation which is used to find the uh, uh, band gap of band gap of a material. Here, the alpha h mu is represents the product of coefficient of absorbance and energy of the photon, and gamma is different for different, as we have discussed in the previous slides. Then the conduction may undergo direct transaction or indirect transaction. Based on that, the gamma value changes. Next, please. Here A is also constant and h mu is nothing but the energy of photon. Then this from this equation, it is converted into Kubica-Munch function and is plotted on a graph. Kubica-Munch function is nothing but h mu and fr square is plotted against the h mu energy of the photon, and a line is drawn to a tangent of to a point of inflation on the course, and h mu value at the point of intersection means whenever the graph or plot is changing its concavity, a tangent is drawn to it, and wherever the tangent touches the x-axis, that point is the band gap of a conductor. Now next, coding is explained by my friend Shreyas.
Thank you, Madhusudan. Now I'll be explaining the programming part of our project. The programming part can be divided into various individual components. Now I will be explaining the LCD display of the calorimeter. LCD display is a basic for any measuring device. Now I'll be explaining the algorithm used in this program. Firstly, start. This indicates the start of the program. Second is turn on LCD. This makes the backlight of the LCD to turn on. Next, clear the LCD. This clears any data previously stored on the LCD. Next, set cursor in LCD. This sets the cursor in the LCD to first row and first column so that we can print on the LCD. Next, print in LCD. This prints in the LCD of first row and first column. Delay. This gives a time delay of 1.5 seconds before performing the next operation. Next is world. This step prints world in the next column. Next, again, delay of 1.5 seconds before executing the next code. Clear LCD. This again clears the LCD. And again, this is a loop, so it again starts from the beginning. Now I'll be explaining the working model and actual code of this LCD display. Here we can see the various components, various electronic components on the board. Firstly, we have Arduino Uno, which is the microcontroller. Then we have a breadboard, which is used to provide connections to connect between Arduino and the LCD display. And we also have an LCD display, which we will use to print the code. Now the code. So as seen before, I have shown the algorithm. Now here's the actual code written for this program. Firstly is include. It includes the liquid crystal library to the program. Then these are the pins defined for the LCD 12, 11, 5, 4, 3, and 2. This can be seen on the Arduino as 2, 3, 4, 5, 11, and 12. Then void setup. This begins the communication between the LCD and the Arduino. And again, it clears any previous data stored in the LCD. Now in loop, we have print hello. Then again, we give a delay of 1.5 seconds. Then again, the set cursor to the next column and again prints world and again gives delay of 1.5 seconds and it clears it. Then again, this loop keeps repeating. Now we will see the simulation of this program. So as discussed before, it prints the word hello and gives 1.5 second delay and again prints world and it keeps on continuing. Now I'll be explaining the second pseudocode. So here we will obtain the values from the photoresistor and display it on the LCD. So this starts the starting of the program. Next is we define the pin A0 as signal pin and we store the value of 0 in a variable called signal value. Then again we create another variable and we store value of 1.1 in analog reference voltage. Then we begin the serial communication with the LCD and the Arduino. Next, we begin the communication between the LCD and the Arduino. Again, clear LCD. This clears any previous data stored in LCD. Then we assign the value obtained from analog read to signal value, and we set the cursor of LCD to first row and first column. Next, we perform a mathematical operation here, which as seen multiplies the signal value obtained from the signal pin A0 and multiplies it to 1.1 and the product is divided by 2. This value is stored in signal value. Then this signal value is made to print in the LCD and we give a delay of 0.5 seconds and this loops keeps repeating, and after 0.5 seconds the sensor will be taking the values and it will be displaying on the LCD. Next part will be explained by Chirag.
Thank you, Shreyas. Now I will be explaining about high-pass filters used in the construction of Arduino board photometer. The main characteristics of this high-pass filter capacitor is that it do not allow all the input signal to pass through it until there is a certain cutoff frequency due to the high capacitive reactance. After that point, it will allow all the input signal to pass through it due to the short circuit. The next slide, please. Next slide. This is the graph which explains us about the frequency response of the high-pass filter capacitor. Up to the certain frequency till the cutoff frequency, there is a certain increase in the output. After that, there will be a constant output voltage. Next slide. In phase 2, we will be doing the working model of Arduino board based LED calorimeter. And thank you for watching.